Acid-base reactions are the fastest reactions in chemistry. Whether it's adding an acid to a solution, adding a base to a solution, or mixing an acid with a base, the creation of a proton or a hydroxide happens pretty much instantly. In this first slide, I'm giving you two general equations. The first one being a strong acid, and the second one being a weak acid. Strengths of acids and bases are a reflection of what percentage of the sample ionizes or dissociates into ions. HCl, or hydrochloric acid, is a strong acid because when dissolved in water, it's assumed that every single molecule of HCl will dissociate into chloride and hydronium. Acetic acid is considered a weak acid because only about 5% of it dissociates when dissolved in water. You cannot tell just from the equation if an acid is strong or weak because by the looks, if they both are doing the same thing. More information such as pKa value are necessary to determine the strength of an acid. I have been trying to think of a water molecule in terms of a salt of H plus and OH, and it has helped me to understand better the reactivity of acids and bases. Some bases and salts of hydroxide, so you can easily tell that they would produce OH when dissolved in water. These bases are also considered to be strong because every molecule will liberate its hydroxide. Weak bases are more difficult to identify unless given an equation. In this slide, we have magnesium hydroxide salt being dissolved into water to produce 2 hydroxides per mole of salt. Next, here we have listed is ammonia, where my water as a salt idea helps me understand that ammonia is going to take an H positive from water and leave OH, which helps me visualize that is a base. When acids and bases react together, this is known as a neutralization reaction. It is called this because the acid and base render each other incapable of affecting the pH any longer, and the solution approaches a neutral pH of 7. In this experiment, we are essentially neutralizing vinegar and baking soda. Vinegar containing the acetic acid and baking soda containing the sodium bicarbonated salt. The reason we are able to give this propulsion to a plastic bottle, however, is not just because of the neutralization, but what a reaction may come after it, which is a gas-forming reaction. Once the bicarbonate reacts with the acetic acid in vinegar, it produces carbonic acid. This carbonic acid is essentially a molecule of water and carbon dioxide stuck together, which at this point may separate back into their normal forms, unless we have a very cold solution or one under high pressure. This is the same reason we hear a hissing sound when we open a bottle of seltzer or soda for the first time, because of the rapid decrease in pressure causing the carbonic acid molecules to revert back into water and carbon dioxide. The same thing is happening here when we mix the vinegar and baking soda. Carbonic acid is formed after neutralization, and the solution is hot enough and was low enough pressure that the carbon dioxide is released from the solution, dramatically increasing the pressure inside the bottle. Eventually, the bottle cap bursts and the bottle goes soaring. Results for this interactive experiment were not quite as predicted. I did something similar when I was a kid by mixing Mentos with Coca-Cola and got a similar result. In both cases, since acid-base reactions happen so quickly, the pressure inside the bottle increases dramatically and almost instantly upon mixing the ingredients together. In this case, as explained before, once the acetic acid and baking soda react with one another, the carbonic acid decomposes into the water and carbon dioxide. The carbon dioxide escapes the solution as a gas and begins to build up enough pressure to blow the bottle cap off and propel the plastic bottle. In this case, I didn't add enough vinegar or baking soda, or I simply tightened the cap a little too much. I added the baking soda in a little paper towel parachute, tightened the cap, and threw it into my backyard as I felt already the gas building up inside the bottle almost instantaneously when I squeezed it. I stood far away for a few minutes as I was actually afraid that the bottle cap might shoot off and hit me in the eye. After grabbing some eye protection, I went back to the bottle and unscrewed the cap to a loud hissing noise as the gas escaped. But unfortunately, there was no CO2 powered bottle rocket created by this backyard lab experiment. Overall, it was a great learning experience and I enjoyed it.